Anyone, any questions so far? Anyone, please? Online, you're okay? Okay, yeah, okay.
Yeah, all
Right.
good.
Yes?
All good, thank you.
Oh, good, okay. Okay, the next thing I want to explain to you is what do we mean by stress X? Okay, I'm going to explain to you what do we mean by stress X. I'll let you guys finish copying first. Okay, I'm going to start on a new page. What is sigma X? Okay, you see, we are trying to find sigma X. What do we mean by sigma X? Okay, so again, I'm going to construct the structure. Same thing like before. Point A, point B. One end is pin, the other end is on a roller. At point C at the center, we have a load P. Okay. So what do we mean by stress X? So I'm going to draw our transformation. This is X, Y, rotation about Z. Okay. So if we were to look at point C, so if at point C, I'm going to put an element. Okay, I'm going to put an element. So this is an element. So in real life, what is an element? Okay, in real life, so I'm going to expand this. Okay, so this is an element. So in real life, what is an element in the physical world? Okay, it's basically you can put strain gauges. Okay, so you're measuring. This is a strain gauge. Measuring the X direction. This is the strain gauge. To measure Y direction change in strain. Okay, so you will change, you measure the change in strain in the X direction. This will measure the change in strain in the Y direction. So now you know the strain, right? You can relate to stress. Okay, so I will not teach that part. Okay, so I'm just trying to explain to you physically what's an element. Okay, so now if I were to draw an element again, right? So this is the element. Right? So from the element, we can get stress in the X direction and the normal stress in the what? Y direction. Okay, so our transformation is still the same. Okay. So stress X means stresses in the what? X direction. Okay, so that is what we are calculating. We are going to determine the stress in the X direction. So remember about the shear, yes or no? I taught you guys shear already, right? Did I teach you guys shear already? Yeah, right. So in shear, we call this what? Shear intersecting planes X. Shear direction is shear force in the Y. Shear intersecting plane is the Y axis, and the shear force is in the X direction. Okay, so now we have normal stress. And the normal stress component is easier to understand when compared to the shear stress. Okay. So as I said before, we are finding X stress in the X direction. So normal stress in the X direction. So now I'm going to draw the cross-sectional view. Okay, so I'm going to now draw down the line over here, a chain line. Okay, and this is my chain line. Okay, so now we are going to sketch the cross-sectional view. So in the cross-sectional view, this will be my Y, this will be my Z, then we have our rotation in the X. Okay, so for this case, we are going to take the example where our cross-sectional area, our cross-sectional view is a rectangle. So this is our cross-sectional, 1, 2, 3, 4, 5, 6, too much. Okay, so this is our cross-sectional view. Okay. So when we have a cross-sectional view, again, if I come back to this, the diagram on the top left-hand corner, at the top, I call it point alpha. At the bottom, I call it point beta. On the cross-sectional view, at the top over here is what we call alpha. At the bottom over here is what we call beta. Okay. And then if we have bending moment, or for this structure, the bending moment will be in this direction. Right? So this is our MZ. That's our MZ prime. Right? So now I'm going to draw our centroid. Right? So by looking at the moment vector, the head of the moment vector is in compression, here it's in tension. So this will be in compression. And the bottom will be in tensile. So what I'm going to do next is to sketch. We're going to sketch the normal or stress X distribution. Okay, we're going to sketch the stress X distribution. Okay, so we are going to draw a line. So this line corresponds to our normal stress in the X direction. And we're going to draw a vertical line. This is where we have our Y. Okay, Y is the distance from the centroid. Okay. So at the center is 0. On the right side, where it's positive, this is what we call tensile. Okay. On the left-hand side, towards the left, we have negative normal stress. We call it compression. Okay. Now, in this diagram, I want you to view it this way. Okay. Along the y-axis, where I'm going to shade in yellow now. Along the y-axis, this is the location of the material. Okay, so I want you to imagine in graphing, that center line over there, that vertical center line that you see, is your material. Okay. Now, why is that important? Bear with me. Okay. So when we plot the graph, the normal stress distribution, you see this. Okay. So this is equal to our minus stress X max. Over here will be stress X positive max. Okay. So that is how the normal stress distribute. Okay. Now, next, I want you to sketch the vector of the stresses. So what do I mean by that? So I'm going to focus on this region now. We're going to focus on this region now. Okay. So we know that this region is going to induce a compression. I repeat again, that region is going to induce a compression. So compression means what? The yellow vertical line is so-called the location of the material. Compression means the normal stress vector is pushing into the material. Okay, so it is pushing into the material. Okay. So that's why we have this compression loading at the top, or Y positive. Then at the other end is pulling away from the material. Okay, so again, location of material, and then the arrow they have just drawn. Okay, they're just drawn in blue. Okay, is pulling away from the material. Okay. And I want you to see something. Okay. On this line over here, I'm going to draw a thick line. On this line over here, right? Right? Or wrong. Yeah, on that line, you can see that our stresses, our normal stress, is equal to what? 0 at that Y location. Right? So what we realize that at this, when stress X is equal to 0, is also known as our neutral axis. Okay. So the neutral axis is where the normal stress is equal to 0. Okay, or stress X is equal to what? 0. The centroid axis is a function of geometry. So i.e., for this case, where we know that this is a centroid, the area at the top and the area at the bottom is equal. Okay, so the first thing that I'd like to drive into your mind is this, that for symmetry, centric, loading. Okay.